Welcome, everyone. This is the Week Hive community meeting, and we have an invited speaker, Rodrigo Bruno, who is an assistant professor at the University of Lisbon, who is working on operating systems and the co-design of the cloud systems and programming languages, doing some exciting work on the serverless computing front, which we are very excited to hear about today. So Rodrigo, please go ahead.
All right. So hi everyone. Thanks for having me. It's a pleasure. So today I'm going to talk about this very recent project that we have started recently, and it's about WebAssembly execution environment for elastic, scalable, and efficient cloud applications. And actually, I'm going to start by the second half of the title about elastic, scalable, and efficient cloud applications, and explain why it's still an important topic to these days. And I'll start by actually looking back and going over the end of Moore's law. That, as we all know, this is basically a big change in paradigm that we used to have developing in applications for a long time. In the 90s and the early 2000s, we had a very good improvement in CPU performance over the years, and then this started declining. And recently, as of, for example, 2015, as we have here in this plot, now we cannot expect any more significant improvements in single core performance. And this has kind of created a big impact on several areas of computer systems. So one of such impacts was on software engineering. Back in the day, we used to have our large applications, our applications built into monoliths, and then we started having the need to actually decompose these applications into microservices. And now we are seeing that these microservices are being further decomposed into functions. And this is a way to actually achieve better elasticity and scalability as a way, or through functional decomposition of our applications. In short, this makes sense because our applications are composed by different modules, and these modules don't scale or don't have the same needs in terms of elasticity. And by decomposing, we allow different components to scale at different rates. We also had an important impact on infrastructure management. Again, we started with monoliths being deployed on VMs in infrastructure as a service. We would start and stop each instance almost by hand. Then we had container as a service. We started having container orchestration systems that will help us scale our platform. We would still need to specify when to scale and how to scale, but at least this would be done automatically later on. And now we are seeing function as a service and serverless, where scalability is completely off the hands of the developer. It's completely managed by the operator. And we see that as we move towards this more automatic scalability, the lifetime of these instances also diminishes. We go from days in VMs to hours, or perhaps a few days, to actual minutes or even seconds in serverless. Still on infrastructure management, but on a different angle, we also see that more and more we are delegating more responsibility on the operator. For example, in infrastructure as a service, we would run on top of virtualized hardware. Container as a service, we would run on top of a virtualized operating system, for example, running multiple containers on top of the same operating system. And then now with function as a service, the interface to the user is already the language runtime. Whenever we use, for example, Apache OpenWhisk, which is an open source serverless platform, or we go to a cloud provider such as Amazon that has their own offerings, such as Lambda, we can pick the language runtime, and this is the entry point. So we're seeing that more and more we delegate more components of our stack into the cloud provider. And this is good because this frees the developer, or this lifts the burden of the developer from handling the infrastructure, but at the same time, this creates some challenges, as we're going to see in a couple of slides. So let's take an example of a feature extraction application, right? So it's an application where I send an image. For example, here I have a cat, a unicorn cat, and this goes through a process of a feature extraction, classification, and in the end, the program classifies this correctly, right? We could think of this as being a microservice application or a serverless application. It really doesn't matter for the example. Now, if I want to use a cloud platform to actually run this application, I would have perhaps two scripts, one for the first feature extraction and one for the classification. Then I would bundle it together with, for example, PyTorch or TensorFlow or any other machine learning framework, and NumPy as well. It's usually kind of this two combination of dependencies together. We would package this and we would send this package over to the cloud operator, right? And then eventually when our function is invoked or our microservice is invoked, the cloud operator deploys one instance and this instance runs on physical hardware. So this is usually how people run applications in the cloud. Now imagine that some of these machines in the cloud provider have some specialized hardware. Imagine that, for example, there is an AMD GPU or an NVIDIA GPU, and perhaps the third machine has a CPU, but it has some advanced instructions, for example, AVX, right? The problem is that on the user's perspective, all of these aspects on hardware and deployment, these are hidden inside the platform. And the user has no visibility over which version of PyTorch to pick. PyTorch releases several different releases, one that is specialized for GPU, one for CPU, and perhaps even one for different versions for different GPU devices, right? But the user has no visibility over this. It might pick one of them or might pick the most traditional one, which is just to rely on the CPU. For example, another quick example is if you install TensorFlow on your machine using Python, TensorFlow will happily say, well, it doesn't come with support for AVX instructions, these vectorizing instructions, and you would have to build TensorFlow against your local hardware to actually make sure that TensorFlow is optimized to run locally. So, in other words, if we use a release that is generic, it will not run as fast as a version of TensorFlow or PyTorch that's compiled toward the specific hardware. The same problem also, or a similar problem also happens on the provider side, because now the provider has a package that can only run on some part of the infrastructure. So for example, imagine that there are AMD GPUs that are idle, but the user decided to upload a package that is only compatible with GPU devices. And now the provider needs to have some unoptimal distribution of workloads. Now, again, another side effect of this problem is that, well, now we are packaging PyTorch and NumPy and perhaps other dependencies, but these dependencies will accumulate and will create large payloads. And this is a problem not only because we have a single user, but because we might have many users. And these many users are actually shipping similar payloads that traverse the entire infrastructure, since from the machine of the user uploading to the cloud platform and internally inside the cloud platform until they actually arrive on the destination machine. Yet another example is, for example, if we have feature extraction and classification running on a different machine, usually this requires some sort of communication. Example is to use gRPC. It's a very common transport framework. For example, when you use Thrift, this will come automatically to generate gRPC endpoints. However, when you actually run the two components on the same machine, since you already took the decision of using gRPC at build time, because you didn't know if you're going to run both in the same machine or not, then if you actually get lucky and run both components on the same machine, you actually still need to use gRPC. We actually looked into the Dead Star bench in the social network use case, and we compared a monolith version that we built out of the Dead Star social network against a microservice version, which is their stock version, where we put all the microservices running on the same node. So this is a comparison of running all the microservices on the same node or having a single monolith in a single node. And we see that there is a 33% improvement in throughput or requests per second that is still on the table if we actually transition from something that uses a local gRPC to something that uses local function calls. So this is, again, because we need to decide the transport framework before we know actually the deployment decisions that are going to happen. So in sum, one of the problems that we identified is that there is this kind of barrier of infrastructure and awareness that obfuscates efficiency. One side is that users do not know the target hardware and they cannot specialize the code that they are actually shipping. And the second is that they don't know the placement, if these components are going to run on the same node or on close vicinity, or if they're actually going to run on very far away nodes. A different problem that we also looked at around the same time is the virtualization performance landscape. And we started by measuring the startup latency and memory footprint of different virtualization approaches. We have the usual Docker, Firecracker, and QEMU that are very common when used in the cloud. And then we have the traditional runtimes for Python, JavaScript, and JVM. And then we also have checkpoint restore and fork as optimization for some of the above. And we also looked into how providers are now building these different offerings, and we see that both Amazon, Azure, and Google Cloud, they are now having an extra fine granularity for billing. They are actually billing by the millisecond and almost by the megabyte. And this actually means that all or most of this chart that I'm showing here is now considered an overhead because they're actually being billed for the amount of time that you're taking to deploy Firecracker to launch JVM. Some of these approaches, they could be solved by having a pool, and this is something that cloud providers actually do. They do have a pool of, for example, they could have a pool of Firecracker instances running Linux, since they know that most of their, for example, service offerings on Amazon Lambda will run on top of a specialized Linux distro, so they could have a pool of these things. But the same is not true for language runtimes, because this is actually very hard to bypass the initialization time of a JVM or Node.js or CPython, because this depends on the application that is being launched. The hard part of the long initialization time is loading the actual application code and start running it inside the runtime. And this is something that we cannot do ahead of time because there are many, many applications. So the goal would be now to actually, okay, can we actually push this startup time and the memory footprint to something that goes from the millisecond scale and megabyte scale to the micro and kilobyte scale? And we're not the only ones think about this. I mean, there are different technologies that already allow these lightweight sandboxes. For example, V8 has isolates, GraalVM has isolates as well. WebAssembly has the concept of a sandbox, so you could have different sandboxes that will deploy very, very quickly and very low amount of memory. And there are already some cloud solutions that allow you to deploy codes, not in using VMs or Docker containers, but actually using sandboxes. By the way, so if you have any questions, just feel free to stop me. I mentioned this before, but I'm just remembering that if you have any questions, just stop me. So one of the limitations that we saw for the adoption of these sandboxes is actually because we have what we call a Linux execution environment, which is an expectation that applications have when they're deployed in the cloud. And this is an example of a Linux execution environment. We have 3 applications, and these 3 applications take advantage of 2 libraries. For example, application A uses library 1, application B and C, they use library 2. And there are really quite a few problems from the start that prevent the usage of these sandboxes. One is that without any external effort, applications would have access to memory. And this is, again, because we're running in a single process. We're running multiple sandboxes on a single process. So we would have to be careful not to allow applications to interfere with the memory of each other. Inside a single process, there is also no mechanism to automatically prevent applications from sharing the same library, and this is a problem because library can have internal state that would be shared. And then there is also a lot of external exposed states inside the libc and the kernel. Applications share the same heap. There are global variables and global functions that are shared across sandboxes. And inside the kernel, well, there is the page table, obviously, but there is also signal handlers, there is the network stack, there are file descriptors, and so on. Some of these could be isolated using namespaces, but there are others that are more complex to actually separate and to hide. So in summary, the Linux execution environment is also imposing limits on the scalability and elasticity, especially because it forbids us from going into sandboxes or using more sandboxes. And in sum, just to summarize these two problems that I've been describing so far, is that we identify there are a couple of misplaced abstractions that stand in the way of performance. And this happens when we're trying to use cloud platforms. On one hand, there is a transparent infrastructure management, which is great for developers, but it hampers the use of optimized hardware and it prevents the use of efficient transport frameworks, as we have discussed before. And on the other hand, applications have the expectation that it will have a full standard Linux execution environment. And this prevents you from increasing the density of your deployment because you cannot use these sandboxes. Now, I'm not going to go into detail about what would be the landscape of alternatives that we have here. We could think about new hardware. We could think about new operating systems, new versions of libcs, new languages, and new frameworks. And we could all try to devise or at least handle part of the problem using different combinations of these techniques. Again, for the lack of time, I'm not going to discuss all of these in detail, but so far from what we analyzed all of these solutions, there is no simple way to actually achieve and solve the problems that we have identified in these misplaced abstractions. So this is why we are thinking about a new way of packaging and deploying applications in the cloud. And we are kind of targeting replacing the Linux execution environment as the target expectation that applications have by what we call a WebAssembly execution environment. So I'll quickly say a few words about WebAssembly just to introduce it. I think this is not going to be extremely new to anyone, but nevertheless. So WebAssembly is this new compact, portable, and hopefully verifiable instruction set. So it's a virtual instruction set. It's designed to be efficiently mapped to a real instruction set, so that the overhead of running WebAssembly is very low compared to running a native instruction set. There is a huge industry and academic push behind it. There are many languages that are now compiling into WebAssembly. Initially, the goal was to actually run on web embeddings, meaning that you could run your Rust favorite or C favorite application on your browser. But now there are many use cases for actually running WebAssembly outside the browser and use it as a sandboxing tool for applications. I leave on the top right the link for several example use cases of WebAssembly right now. So WebAssembly is, as I was saying, a target for applications to compile into. So you can compile, for example, C code into WebAssembly, and WebAssembly is designed to be efficiently then converted into a native representation if needed. And finally, WebAssembly runs on top of a linear memory layout. Again, this is a sandboxed instruction format. It runs everything is an offset inside a linear memory. And it runs on top of a stack machine. Instructions, they will use a stack to push and pop arguments, and they will have their heap to load read or write values to memory. So coming back to the WebAssembly execution environment, so the question that you might be asking right now is, well, is WebAssembly already enough to actually fulfill the problems that we're looking for? And the answer is unfortunately no. WebAssembly is right now evolving towards something that looks really similar to a Linux execution environment. It's possible to have applications built into modules, but they are statically linked right now. It's possible in the future they will become dynamically linked, but right now the expectation is that this dynamic linking will still expect all the modules to be local. And this means that you would still have to package and link all your application and dependencies before you actually upload any package to a cloud provider. WASI also is the system interface for WebAssembly, and it's also heavily inspired in POSIX, and we're going to discuss this in a second. And by doing so, it again heavily imposes limitations on the use of sandboxes because it exposes a lot of information from the libc and the kernel. So going into the execution environment itself that we have in mind, so the idea is to take a step away from the traditional Linux execution environment where we have applications and libraries and define everything as a module. So all the applications and all the libraries, they are independent modules, and the modules, they are independent from one another, but they still can interact through interfaces. And these modules are named entities. Modules can request handles to other modules. Modules can actually be stateful or stateless, and this is basically a hint so that the operator can decide to deploy additional replicas of a particular model or not. This is similar to how, for example, function as a service platforms operate, and even microservices. So microservices are expandable, they can be killed and restarted. Other microservices that might be deploying, for example, databases, they are stateful and they cannot be easily destroyed and replaced. Cross-module invocation is supposed to be opaque, meaning that modules do not see or cannot assume that a particular destination model with whom they are interacting with is a local or is a remote. And this is an important distinction because this will allow the platform to actually optimize the transport or the communication framework that is used at runtime. We are also working on something that will be a replacement for WASI or an improved version of WASI that is actually a portable version of WASI. So again, POSIX, it has P in the name for portable, but this is portable at build time. It means that if you build an application against POSIX standard, it should be able to run on different platforms, but it doesn't mean that after you run it, you're going to be able to checkpoint and restore it later, for example, or you're going to be able to run multiple instances of different applications running side by side. So this is what we call portable at runtime, and this is actually the goal that we are aiming at. We want modules to be portable at runtime. We want multiple modules to be able to execute safely side by side. These modules are going to take advantage of a system interface, and the system interface provides an opaque access to the rest of the platform. The idea is that we're going to avoid having, for example, files and sockets, the concept of a file and concept of a socket, but instead we're going to offer only the concept of streams of data. So modules can open streams of data from external resources or from other modules, and these streams of data will not reveal or expose the origin of the data. The origin of the data will be another module, but again, you might not know if this module is running locally or remotely. So again, and finally, the third component is to have a module registry. The idea is that WebAssembly modules in WebAssembly execution environments are deployed and linked independently. These modules will come from a shared module registry that is not only used by developers to upload their modules, but could also be used by the cloud operators to actually offer versions of specific modules that are optimized for their specific infrastructure. And we're going to see how this could be leveraged to actually employ an optimized version of, for example, PyTorch, as we have seen before. Obviously, we could have we're going to look into all the traditional lazy loading, caching, and chunking optimizations of registries. Physical machines might have caches of this module registry, such as that you don't have to pay the price of fetching from a remote registry and so on. So an interesting analogy to look into this module registry and the way we are trying to use it is whenever you're building application or an application that is based on JVM, you might use, for example, Maven, and Maven will pull all the dependencies that are required from a remote registry at build time. What we're aiming to do is to actually have sort of a Maven that runs at runtime. So whenever you actually try to open a module or try to open a piece of code, this will actually trigger a fetch from a remote registry or from a local cache. So coming back to the previous example, where we have our image classification example that builds against PyTorch and NumPy into a package and sends it to the cloud. Now with the new environment we're proposing, the idea is that you only ship the actual source code of your two functions or your two microservices, and you build them into two separate modules. And you can assume that the module registry will already have versions of the most popular modules. I mean, you could also push a version of PyTorch and NumPy, but most likely this registry would already have NumPy and PyTorch available. And not only that, but the cloud operator, knowing its own hardware, would also have a module version that is compatible or optimized for the specific hardware. Again, the goal is that modules, they do meet at the interface and they have an interface that is the same. They do implement the same interface, but the implementation can differ depending on the target platform. So here the user would ship the two snippets of code. This would be installed in the module registry. And whenever an invocation is done, the cloud provider would actually place this code running on, for example, an NVIDIA GPU, or if it has available AMD GPUs, it could also an AMD GPU and instead pull the PyTorch version that is specific to AMD GPUs. This has two benefits. One is that it's optimized for the correct hardware. You decide which hardware to use at runtime, and you install correctly optimized for the target hardware. And you also reduce package duplication. You're not uploading multiple versions of PyTorch that are hidden inside a zip or a container image of your application. On a similar vein, remember the example with the feature extraction communicating with classifications through gRPC. Now, with WebAssembly execution environment, they are using a system interface that is opaque to communicate with another module. And the idea is that behind the scenes, we might still use gRPC if these two modules are running on remote machines. The difference is that if these two modules run on the same machine, then feature extraction and classification will actually procedure call. And this might be as fast as a function call in C or C++. Again, we are deciding or we are delaying the decision of which transport framework to use until we deploy the actual code and we know the placement of different components. And also by doing this, we are also allowing high density sandboxes to be used, because WebAssembly modules can be placed on the same machine using the same process in different sandboxes. So just to wrap up, so the idea or what we're targeting is that there is currently a couple of cloud abstractions. There is this lack of visibility over the hardware, and there is this expectation for the Linux execution environment that are obfuscating performance. And this prevents a good match from what applications actually expect in terms of performance from the performance that they actually get. We are seeing that WebAssembly could become this new cloud abstraction. There is a huge technological push. There is a lot of industry momentum going behind and actually investing a lot of time in porting more and more applications, more and more languages and more frameworks into WebAssembly. And I think this creates a pool in our community, a pool in terms of research that we should take advantage of, and we should try to use it to improve how we utilize cloud resources. And yeah, so WebAssembly modules and WebAssembly execution environment, they're lazily linked by the operator after deployment, and this creates opportunity for optimizing behind the scenes. So again, we are not removing abstractions. We are just placing abstraction in a different place by delaying application linking to deployment time instead of doing it at the build time. So that was basically the idea that I had prepared to discuss today. So thanks a lot for your time, and I'm happy to discuss. And if you have any questions, I'm happy to answer them.
Thank you, Rodrigo. Very interesting talk. Yeah, in fact, we were also thinking about revisiting the container abstraction as the main deployment abstraction, and which basically packages everything, including the rootfs, OS, everything, and sends it everywhere pretty much. So that's a major overhead.
Mhm.
We haven't looked at WebAssembly yet, actually, but it's been like we have discussed WebAssembly with different people. So yeah, it's really interesting that they introduced these WebAssembly modules, and it seems that the whole ecosystem is going towards like more general, like supporting pretty much everything.
Yeah,
I'm actually wondering, like, do we actually need to support everything? Where do we need to stop? Or we just need to wait until WebAssembly community builds everything literally, and then we just kind of use it?
um, so that's a good point. I mean, I think right now WebAssembly is still very in the early days. There is not a lot of things out there already robust. I mean, there are many languages that you can already compile, but the support inside those languages is still very limited. So I think we're still kind of a couple of years away from running decent applications on WebAssembly. So the ecosystem is still ramping up. Yes, they're heavily focusing on WebAssembly modules as a kind of a unit of separation between applications. And the idea is that you can build several modules inside the same process. Modules are independent and then they have interfaces. Now, I think there is already enough out there that we can show and we can build a platform such as the one that I'm discussing here. We can show kind of examples and proofs of concept. Yeah, but I think the community is still getting there. For example, models are still statically linked. They cannot still be dynamically linked. This idea of having a registry, I mean, this is something that is obvious, but no one has still built this. There is, I think, one project that is still experimental, is trying to build something that looks like a Maven for WebAssembly, but this is still targeted at at build time and not at runtime. So I think we'll still have to wait a little bit more, but there is already enough to see what's the potential of WebAssembly. And the cool thing is that WebAssembly is easy to verify because it's a very simple instruction set. You can actually verify that it's correct and it's not kind of allowing cross module accesses and so on. So it could kind of serve as a new, I would even envision it as a kind of a replacement for containers or even VMs, because you can, if users deploy WebAssembly modules, you can actually verify that these modules are not going to escape. And if you have a visor, like a hypervisor layer that is simple enough, and it could also be verified, then this could be a practical replacement for VMs.
Well, the thing is that ultimately at some point you need to, I don't know, do networking or something like this, and then you need to engage the kernel. Like if it's not the guest, then the host, and then it's kind of the same problem. Unless you push the whole modules idea down to kind of microkernel level, right? And then
Yeah,
start leveraging communication across modules inside the kernel, but that's a whole different story. We've been there already.
yeah. I mean, you could think about this problem in different ways. You could think of like, okay, so we're just going to use WebAssembly, and then underneath we're going to have namespaces, such as what containers use. Or you could think about rewriting completely libc and having a virtualized version of libc. I mean, these are still options on the table. I think in the user space, we're going to offer this module abstraction, and users will not be able to open sockets directly or open files directly. They're going to use an interface that looks like WASI, or a streamlined version of WASI. And underneath the WASI will have access to sockets, will have access to files, and will have a virtualized implementation, either being through namespaces or through actually handling virtualization in user space. But the idea is that this implementation is completely hidden from the user, and applications that are written by the user, they have zero visibility into the underlying environment. And I think that's where we are trying to push the barrier right now, because when you deploy something, even to Amazon Lambda, for example, on serverless, yes, you start inside the Python runtime or JavaScript, but you can still look into your native environment. You can still kind of probe into the processes that are open. You can still look into your file system. And this is allowing you to actually grip some local environment artifacts that would prevent you from having higher density, because you need to offer a full file system to each of these guys. You need to offer a full network stack to each of these guys. And we're just thinking that this is, for most applications, this is a waste. Applications in serverless, most of the time, they just want to open a connection to somewhere, pull some data, process, and push data to some other destination. And the fact that we have a full Linux execution environment is just an artifact of the technology that we have been using for many years. And we're seeing that now it's perhaps an opportunity to clean up and offer a minimal abstraction. By the way, this is one of the most challenging points in this project, is to find the canonical abstraction that is still expressive enough to implement interesting things, but doesn't allow you to have full access to the system, because otherwise you're back in the original point.
I can also imagine that people really like deploying containers, right? So in terms of deployment abstraction, it's very convenient. But from the perspective of compiling it down to modules and storing modules, that could be probably hidden entirely in the infrastructure. Then people don't need to rewrite things.
Yeah, I mean, we are not, yes, so I think this could be completely automated. I mean, WebAssembly is already kind of hidden. You don't code applications directly against WebAssembly, it's just a compilation target. And we are not, I mean, there are a couple of interesting papers from HotOS and SOSP last year that propose, like, well, we should now compile applications or write applications into a monolith and then allow the framework to actually decide all the distribution. And these are great works, but they're actually trying to change how developers build their applications. We are starting from a different perspective of, yes, we are not trying to change anything. We're just going to intercept a narrow waist that already exists, which is WebAssembly. And this can be done automatically in the infrastructure by intercepting how application pipelines and deployment pipelines operate, and splitting modules and making sure that these modules are correctly deployed, and then linking them together. So yeah, we didn't think how to actually hide all of these details, perhaps behind a compilation pipeline, but yeah, I'm sure this could actually be pushed into the underground details.
Yeah, one more, I think, point that I want to highlight is that the community, like the serverless community, the WebAssembly communities, these are quite different communities actually from like what I understand. And for example, there are a lot more PL people on the WebAssembly community rather than kind of virtualization people who are in the container and VM business of a cloud. So that creates one of the so basically, like coming from the virtualization world, we don't really know what's happening in the WebAssembly world. I don't know
Yes.
if this is what your experience confirms.
Yeah, I mean, this hints at the problem that it's a very interesting problem, which is the two communities are a little bit separated. Like the PL community and the systems community are perhaps separated further than they should be. And yes, so WebAssembly comes mostly from the PL community. This was kind of published in PLDI maybe 2018 or 2019, the original WebAssembly paper. And I think, yeah, I think systems and PL communities should actually kind of collaborate a little bit more. I don't think WebAssembly is a very complicated technology. It's supposed to be very simple, and it's supposed to be actually verifiable, and it's one of the very attractive things. And this is kind of the ingredients that people in virtualization really enjoy. This is why also Rust is coming up to speed right now in many places. And I think this could actually be a new standard or a new way of thinking about virtualization. I'm yet to see someone look at WebAssembly and trying to build a hypervisor built or compiled into WebAssembly. This would be extremely cool. I'm not sure if anyone is actually doing this right now.
Yeah, I totally agree. Actually, NTU recently recruited Conrad Watt, who is an assistant professor here. He's on the board of WebAssembly steering committee, like that. So he's a PL guy, actually. And he's saying that like actually these PL people who are driving WebAssembly, they are very much interested in the system evaluation, like performance aspects of things. Which is, yeah, basically doing someone else's job in a sense. So there is a definitely ground for this type of work. So if you're interested, I can also connect you to him. He's yeah, he just started. It's from Cambridge.
Okay, yeah, definitely. We are also collaborating with Ben Titzer, which is one of the early guys from WebAssembly. He's now in CMU. But yeah, definitely. I mean, I think PL people are kind of more and more interested because now they realize that WebAssembly could potentially play a big impact, not only in web browsers, but actually in the clouds. And in the cloud, what matters is cost, energy, and a lot of performance metrics. And speed is not the only performance metric that matters. So yeah, so I think there's a lot of interesting opportunities. There is a lot of other things that I didn't discuss, but they're also part of this project, such as how to make language runtimes optimized for WebAssembly. Right now, it's very hard to actually run or port JVM or CPython or Node.js into WebAssembly, and there are teams, and we're working a little bit with Ben on how to think about these runtimes specifically to run on WebAssembly. But yeah, so there are a lot of interesting challenges on the road.
Any other questions?
Hi, on slide number 61, actually.
61. Okay, let me go back. All right, this one.
So 62, sorry.
So, all right.
Huh? What?
I guess maybe before this.
Was it the one that has like PyTorch and the NVIDIA stuff at the registry? Yeah.
Maybe.
Sorry. Yeah. So here we can so are we like optimizing this modules for this type of different deployment environment, or are we having this packages like NumPys and PyTorches and stuff as a separate module, and we're doing kind of like a yeah, kind of like a DLL style?
Yes. So PyTorch. Can you see my arrow?
Yes, we can.
Yeah, okay. So the idea is that the cloud provider manages these machines, and it knows the hardware that sits on each of these machines. And by knowing that, it could ahead of time compile PyTorch and NumPy if needed to target specific AMD, NVIDIA, or specific advanced instructions on the CPU. And after doing that, it could actually upload all of this to the model registry. So perhaps this image is not great, but the idea was that this is the PyTorch version compiled to CUDA, PyTorch version compiled to ROC, and the PyTorch that is a standard CPU version. And the user, whenever it deploys a NumPy, for example, a function that uses PyTorch and NumPy, it doesn't need to specify if these modules are going to run on a GPU by NVIDIA or a GPU by AMD or a CPU. This is decided at runtime. Whenever the provider or the operator decides to deploy, it will see which environment is available. It will deploy the Python program, and the Python program will import PyTorch, and only at DL open time, if you want to think that way, the operator will decide which version to pull from the module registry. and this will depend on the local machine that you're actually using. Did I answer the question?
Yeah, I think it was. Yeah, I think it solved my question.
Right.
So I have different question, a bit different, because kind of now we're talking about the kind of baseline libraries, okay, because almost everyone would use NumPy and PyTorch, but what about the modules that use also provides? And one of the points that why GPC is bad, that between these modules, if we just deploy them as set functions, we would have gRPC overhead, even on the same node. Okay. Here, it would be linked together on the same node, right?
Yes, yes.
What about the case when they are placed on separate nodes? Or it's only the case when it's located on the same node?
Sorry, I couldn't get the last part.
So, previous gRPC was useful because it would be run single node on multiple nodes. Like, application is spread out of the gRPC because networking works the same way. But with this syncing stuff, it really could be done on the same node. What about the case when these models might be scheduled or placed separate? Just not the case.
Yes, so I'll try to answer. Let me know if I didn't quite nail it, because I some parts of the question I might have lost. So
Okay.
yes, so here in this example, these are going to run on the same machine, and NumPy compiled, sorry, PyTorch compiled to NVIDIA or AMD. This is still a module, and modules still interact through an opaque interface. So whenever your image classification or feature extraction send requests down to PyTorch, they're still going through the system interface. And this allows you actually to do something that I didn't describe here, which is you could push this this box here, which is one of your Python scripts, to actually a different machine. We could have situations where you have a machine that is only doing CPU work and memory, or it has like a lot of cores, a CPU with a lot of cores or multiple CPUs, and then you have like a farm of GPUs, and you could actually decouple these two things, because they would still communicate thinking that they're invoking local modules, but locality is a notion that right now is lost, because you interact through the system interface, and the system interface is the one that knows if you're local or if you need to go through the network.
Yeah, that's exactly what I was talking about. Yeah, it's kind of this system interface is a killer feature in a sense. It kind of it would know where to route this request even on the level, like instead of gRPC, it would either route directly to like call in the module without the networking part essentially, or
Exactly.
wrap around into some networking packets and send it to a different node and run it there.
Exactly, yeah. So this might seem like incredibly inefficient, and it will be if we don't do a careful implementation. But the idea is that if we actually have a way that we can set up, for example, handles, when we want to create a handle for a specific module, the implementation of this handle might be something that calls gRPC, or something that calls directly the destination symbol in the same process. So in practice, if you're running on a local machine, you would have to pay something that is equivalent to a virtual call in C++. So this would be a very, very low overhead, and it will bring you this kind of added advantage that in some cases you are basically running on specialized hardware, and because you kind of you hide all of these decisions behind the platform, and the platform can decide for you. So there is a very small price to pay for what I would say a big advantage or a big potential advantage.
Yeah, thanks. That's exactly what I was looking for.
Thanks for the question.
I actually have another question about WASM. So from my understanding, the WASM was introduced to like kind of speed up web browsers.
Yes.
And then because web browser itself is kind of how to say it? It's kind of like a sandbox, kind of like container, right? So people implemented WASI to give it more system interface access, right?
Yeah.
And then people are pushing towards like more POSIX support for POSIX, right? It's
Exactly.
why at the like end of the slide, you mentioned about POSIX, I guess. So
Yes.
I'm not sure like what's the advantage of WASM over like different VM-based languages like Java and something. What if like someone built a compiler that compiles every code into Java and run on Java JVMs? Is there any like difference between
That's a good
this
question. That's a very good question. So I would say the main difference, I mean, we could think about bytecode, right? Java bytecode, and that's exactly the point. You could say, well, why Java bytecode is not enough? Why can't we just compile C++ to Java bytecode? And the answer is we could probably do it. The difference is that Java bytecode is very hard to map into real x86 or RISC-V or other instruction sets because it has instructions that would require you to do a lot of lower level instructions. It would basically grow quite a lot, and this would require, for example, if you want to do JIT compilation, it would require a lot of JIT compilation. If you want to do interpretation, this would require heavy interpretation. So I think this is one main difference, and that's why you don't see, for example, C or C++ or Rust being compiled to Java bytecode because this bytecode would be extremely slow to execute. Another thing that is a difference is that Java and all the other languages that compile down to bytecode, they do rely on the JVM to do all of this system access. For example, if you write a Java application that opens a file, you would rely on the JVM to go down and open a file, and this would call libc, and then after this libc, you would actually get into the kernel. In WebAssembly and in WASI, what they're doing is they started from scratch and they are building a system interface with the minimal components that are needed. And they're adding file support, now they're adding thread support, and they're continue adding more and more support for other features. And they do this by providing their own libc. They have a toolchain that provides a libc implementation. For example, when you call malloc in C, and you compile down to WebAssembly, this malloc is a malloc that is aware of the linear memory and it keeps everything in check. So we'd have to kind of rethink the whole JVM design if you want to compile something down to lower level execution formats such as WebAssembly.
Okay, so
did I answer it clearly or?
So if I understand correctly, it's kind of like this WASM is kind of like a intermediate language, intermediate representation kind of that was built with this multiple architectural supports and like optimizations and stuff in mind.
Exactly. Yes. So it was built to be easily mapped to a real ISA.
Yeah, I guess it's like completely different direction than Java.
Yes, because I mean, if you, I didn't show it sometimes when I give talks, I show this slide, is that if you look at the Moore's law curve, if I show it here, so if you look at this curve, Java was proposed around this time, right? In the green, we are not caring about CPU performance at all. And if you see Python, JavaScript, C#, all of these languages, they were proposed in this green area. And this is where people were not really looking for optimizing CPU. If you look at WebAssembly, this WebAssembly was already proposed here. So a lot of concerns were already given to performance. And if you look at Rust, was around this time as well, and Go. So as you see language development and proposals, you see that as they step away from this green area, they start introducing more and more trade-offs between developer productivity and abstractions and performance.
Okay, it's kind of like a advent of SSDs, I guess. Somewhat.
Advent of what, sorry?
SSDs, kind of like.
Yeah. Yes, I would say so.
Okay. Okay, thank you.
Thank you.
Junke has a question on the chat, but maybe you can ask your question. Just unmute yourself and ask.
I could
Okay,
try to chat, but I would have to pull this thing up.
she can ask it. It's okay.
Hello. Can you hear me?
Hello.
Yeah.
Can you?
Yeah. My question is, do the slide you showed before, the PyTorch package, the the page.
So which slide? Sorry.
The slide you showed just now on Leonard's question.
The previous slide. Let me see. With the modules.
Yeah,
This
it's
one?
slide. Yeah. So my question is, if we register each model with different set of hardware, will it increase the redundancy of the module registry? Like we have different set of PyTorch instead of only one. It's not the generalized one.
Yes, so that's a good point. So yes, we have different versions of PyTorch compiled to different backends for each one for one specific hardware platform. But the advantage is that multiple users that use PyTorch, they won't have to submit PyTorch again and again. And the system should actually be designed in the way that if you try to submit another PyTorch module for an architecture that we already have in the module registry, it should basically say, yeah, sure, thanks, but it will not actually store it because it knows that it already has a copy of it. So this design hinges on the fact that we will have many more users and many more functions and microservices than we have architectures. That's why we are hoping that we will reduce duplication because yes, we'll have one copy per each destination platform, but we'll have a single copy for all the applications. And hopefully we'll have many, many more applications than architectures and devices that we have locally. Did I answer the question?
Yeah. Thank you.
Sorry, I have a basic question. So when the user submit this function, do these modules need to be loaded from the registry, or these modules are already in different kinds of machines, and then the user module can be directly loaded to a specific machine? And if these modules are loaded from the registry, will there be any overhead by this loading process?
Yes, so that's a good point. So modules, in theory, they come from the module registry, and yes, there will be an overhead, but we can have local caches, and the idea is that each machine could have a local cache of modules that have been previously loaded, or very popular modules that the operator knows that many people would try to use. For example, if I was an operator, I would push NumPy to all of the machines, such that when a user comes and asks for NumPy, I say, well, I already have a local version. So you would have exactly the same performance as if you would bring your own NumPy, or even better, because you don't need to pull NumPy from cloud storage together from your application. So yeah, so a lot of the things that I describe here, if they're implemented without any optimization, they would be incredibly slow. But I think there are opportunities for easy optimizations that would actually make performance, in the worst case, similar to the performance that we now have when we don't have the system. But in the best case, it would be much faster.
I see.
For example, now we would take advantage of NVIDIA or ROC whenever they're available, when before the user would perhaps deploy a CPU version because it doesn't know what type of devices are going to be on the other side.
I see. Yeah.
I actually think this could be a way to allow serverless functions to harness accelerators, because right now it's a very difficult problem to understand how we could expose accelerators to serverless functions. And I think this is because, well, serverless is about you don't controlling the infrastructure, but then how you're going to know which device you're going to run. But if there is this separation and you wait until deployment time to decide which version of PyTorch, for example, to use, then this could be a way to leverage accelerators behind the scenes.
Yeah. Thank you.
Thank you.
Yeah, and this modularization actually can have a set of trade-offs as well. Because, for example, different accelerators may require different type of modularization if you want. So in a sense, like batching images for inference, or like sizing the batch, collocating, disaggregating layers of models, like that there is a lot of trade-offs actually.
Yeah, for sure. I mean, there's a lot of design decisions that we are leaving open. Yes, so there is a lot of bundling and unbundling, or how we could optimize these modules. I mean, these modules, nothing prevents them from being deployed in different virtualization strategies. For example, modules could live on their own VM, or they could live on different processes, containers, or they could even live in sandboxes. Like, none of this, what I've described here, prevents you from being a little bit more conservative for different applications that you could actually go and deploy on different VMs. So this also is a way to support different vendors. For example, my application basically does not use anything that is specific to one vendor, could actually be deployed on a different one, because, well, whenever I import NumPy or PyTorch, I know that the other provider will basically import its own version. So it's a way also to be a little bit more interoperable in terms of architectures and deployments and so on.
And another thing is some of these modules, Python modules can be huge. Like, for example, PyTorch, that's like every time you import this blindly, you import gigabytes, actually.
Yes.
Whether you need anything of this, it's a good question, but still gigabytes. So
Yes.
Some combinations, I don't know, lazy paging, so basically what is a module, what is the format, what kind of chunking, what kind of, I think there are many questions there. For example, for container support for AWS, they chunk up containers. So essentially they keep the containers, but they would chunk the layers into small pieces and then load these pieces, right? But that's file system, and that's kind of brings all the legacy of file system with it, which is not great. Yeah.
Yeah, so we are thinking about doing something. We are going to start with something similar to what Amazon is doing for containers, for sure, with layers, like chunking and lazily loading chunks and whatnot. So this is part of what we have in the plan. But we also see that this might be kind of a smaller granularity that might open new challenges and new trade-offs. Our hope is not to do this based on file system, but actually based on modules. But yeah, so this is, we have a student that's currently looking into this part. This is the registry part of the system that we are looking to.
Yep. Yeah. Right. Yeah, this is very interesting. There are a lot of trade-offs. I think I had a discussion around something like this, like this direction. So one of the questions that was asked is like, okay, what is the benefit you are bringing to the table exactly in terms of performance, memory? Like, we understand that this is a cool system. We understand it's going to be faster, better, whatnot. But what is the benefit we are talking about? So I think that's kind of focusing on one of these contributions, whether it's performance or footprint or something, can pave the way for the whole system to appear, actually.
Yeah. Yeah.
Because this is really, really like big scope, really big scope for one project.
Yeah, I mean, this is a project that there are multiple students working on, and yeah, the idea is to be like an umbrella project with sub kind of branches that are being their own projects on their own. But yeah, I mean, there are mainly two ways that we can show performance. One is deciding which hardware to use. I think it's an obvious way, and we can run a large scale experiment to show that if the provider has the ability to decide which GPU or which CPU to use, rather than being constrained by what the developer decided at build time, I think we can show performance improvement there because utilization will improve and perhaps even efficiency will improve. This is, I think, one area that we can easily show. And the other one is in terms of density. So we can show that if we use sandboxes compared to having everything separated in a container or in a VM, because right now developers are expecting a Linux execution environment, which is kind of this kind of container abstraction where you have your own your own file system, you have your own vision of the system. But this is costly. I mean, booting a full container can take hundreds of milliseconds if you're talking about like namespaces and an operating file system and so on. And this also incurs not only latency but also memory footprint. If we can deploy applications side by side without interference, this is probably not interesting for PyTorch because PyTorch is already a beast. But if you're talking about lightweight applications that do some light HTML processing or do some small shared interaction with the database, then we could pack a lot of these things in a single process, and this would save a lot of overheads. I don't have here results, but I mean, we have measurements that only context switching back and forth across many of these sandboxes, if they are separated by process, this creates a huge impact on performance because you're constantly swapping in, swapping out, and the memory footprint because you're duplicate loading a lot of the components in JVM or Python and so on. So I think this is the second way we can show performance. But again, this is a project we started. We started working on this a couple of months ago, and we have several students working on different fronts. Hopefully, in the next months, I can show you some details with some numbers.
Well, things move very fast, it seems, in your group. 2 months through, 1 month more, and like 3 publications out, right?
Well, we hope. Yeah, I mean,
Yeah.
I'm very optimistic, but yeah. So this will take a little bit of time.
Yeah. So we are actually looking at like maybe not in this particular scope, but we're just zooming into what's happening on the GPU and kind of some kind of partitioning, like just like modules or something like this, just for this specific thing. So just like when you talk about like PyTorch, right? Because yeah, even just zooming into this, like there's already a bunch of stuff to do. Yeah.
Yeah.
So yeah, this is a very good direction. I think it should inspire a lot of people who is going to watch it on YouTube.
I hope so. I mean, I'm happy to discuss. So if you want to like share, brainstorm a little bit, just hit me on email. I'm happy to talk about it.